Cool. All right. So today we're going to start talking about ensemble methods, and that'll cover today and tomorrow. So there's two main kinds of ensemble methods. We're going to talk about one kind today, another kind tomorrow. But before we get into that, I wanted to talk about something with regards to decision trees that will also apply to the models today and tomorrow. And that is one of their attributes from decision tree models. Let me see where I put it. Here, feature importances. I forgot to talk about this yesterday. So really quickly, when we talked about our linear regression model and similarly our logistic regression model, you have coefficients from which you can understand your data through your modeling. From decision trees, you can get something similar. So rather than coefficients, they have this attribute known as feature importances. And how feature importances are calculated is it is basically the normalized total reduction of the criterion brought by that feature. So basically, using that feature, how much more purity can you achieve throughout your decision tree from that feature? So in this example, where yesterday we were talking about, this is the iris data set, the feature importances, and they all add up to 1. There is basically, this graph will basically tell us that petal length is the most important feature here, is basically the feature that helps determine the species of irises. So the way that you get this is after you fit your model, anytime after you fit your model, you just have to pull out the feature importances. Oops, let me just rerun this one. Oh, this one right here. Okay. Oh, there we go. All right. So when you grab the feature importances, is going to give you the number of values equivalent to the number of columns that you have. So the way that you join these importances with your column names, you can pretty much just zip them together. They will be in the same order. So that's how you make use of feature importances. So if any sort of tree model ends up being one of your best features, this is something that's really, really useful to help you figure out, help you learn about your data through your modeling. Cool. I will tell you that today's models, tomorrow's models, they all have feature importances as well, and they work the same way. Cool. Any questions about this before we move on to ensemble methods? Okay. Oh, before I talk about that, the reason why, and I mentioned this about when you're creating your modeling function, which if we go to our homeroom, the modeling function over here, it should return the model. And the reason for returning the model is so that you can access its features. So if you remember, when you define a function, whatever is in the return statement is whatever is saved. So therefore, if you're returning, let's say you're returning model and you run your function and you save your output to a variable, you'll be able to get things like feature importances, like coefficients or predict probability. You'll be able to use the output of your function that way. If that doesn't make sense now, during the office hours, I'll go through a couple examples regarding that. But in your function, you should return the model object. Cool. Questions regarding that? Awesome. Let's talk about ensemble methods then. Oh.
I don't really see it in our version of the 29 decision trees.
Yes,
notebook.
This code is not there because I just added that in. It's pretty much just these 2 lines, but you know what? I will upload an updated version of this later today. Let me make a quick note of that for myself. Yes, thanks for that note.
You could just drop the 2 lines into Slack if you don't mind.
That's true. Yeah, I'll do that. Awesome. Okay.
Thank you.
You're welcome. Let's get into some ensemble methods. Okay, so there are 2 main kinds of ensemble methods. Actually, before we get into that, let me talk some terminology. So first we have ensemble methods, and an ensemble method is basically any method that utilizes more than one base model. So it's just, multiple models working together as an ensemble. There are 2 main kinds of categorized ensemble methods. One is bagging, which we're going to talk about today. And tomorrow we're going to talk about boosting. However, there are ensemble methods that don't fall under either bagging or boosting. For example, let's just say, so far we've talked about logistic regression, k-nearest neighbors, Bayesian classification, decision trees. So let's say we have these 4 models now, and I run my data through all four of these models. And for a certain test data point, let's say it's a binary outcome. And through these 4 models, 3 models tell you that the result is 0. 1 model tells you that the result is 1. One very, very simple ensemble method is just taking a look at the results of 4 models and do some sort of voting. You can do some sort of voting to figure out, okay, if 3 models are telling me that this is 0 and 1 is telling me 1, it's probably going to be 0. It's sort of like, wisdom of the crowd, or, many learners, many models at the same time, rather than just relying on the output of 1. So at its simplest level, that is also considered an ensemble method, but bagging and boosting, bagging today, boosting tomorrow, those are more, I guess, formalized ensemble methods, just in case you're wondering about terminology. Okay, so let me clear this. Okay, so to do a quick review of regression trees, this is basically one of what a regression tree does. Actually, let's talk about classification. Let's talk about classification instead. Okay, so in classification tree works the same way. You're basically figuring out best thresholds per feature, and only one feature at a time, to divide or segment your feature space. And so this is the example that we talked about yesterday, where our decision tree model figured out, okay, a good partition to start with, or the best partition to start with, is at x2 is less than or equal to 2.45, whether it's true, false. If it goes true, you can see that this terminal node is already pure with class 0. And then from here, you split again at x2 greater than or less than 4.75, and you keep traversing down the tree. So that's how a decision tree works. Here we go. All right, so if we visualize classification decision trees, this is how it looks in feature space. So if you imagine this is just 2 features, let's just say that there's an X and there's a Y, X and a Y. The more depth you have, the more segments in your feature space there are. And this kind of goes back to what I was talking about yesterday when we have max depth. If you have very high max depth, you can easily lead to overfitting. However, if you don't go deep enough, you are terribly underfit. For example, you can see here, in this depth equal to 1, you pretty much only have 2 segments. You can only have one of 2 different outcomes. And then depth equals to 4, you start to get more and more granular. So tree depth and overfitting. The deeper our trees go, the higher the chance that we overfit our data. And so this is an example of some data. So the actual data are these orange data points over here. And we have 2 lines. I know it's not super easy to see, but we have 2 lines going on over here. We have a light blue line that tracks like this with a max depth of 2. And then we have this green line that, as you can see, is kind of like fitting to these data points down here. This is a max depth of 5. And so you can see that very quickly, you can start to overfit a decision tree. And that's actually one of the biggest downsides for decision trees. All right, so trees are pretty great.
A quick question.
And,
If you were to run a grid search with like 1, 2, 3, 4, 5, would it automatically adjust for the overfitting? I don't know if we discussed that earlier.
That's a good question. So grid search, and I guess I haven't really talked about how to run a grid search with regards to train test split. But when you run your grid search, you're running it on your training data. And even though it's doing cross-validation within your training data, so let's say, you have 80% of your data in your train set, and you do cross-validation of 5, every fold it's going to do like, 16% each. That does help with the overfitting a little bit, because it'll choose the combination of parameters that over the 5 folds, you get, the best average metrics. However, you still have the tendency to overfit to your trained set. So let's just say that 20% that you held out for your test set, decision trees have historically shown that, yes, you can still do your grid search, and it does make the overfitting a little bit better, but for a lot of people, not good enough. But yeah, grid search will definitely help, but not to the degree as like using an ensemble method, which we're going to talk about in a little bit.
Thank you.
You're welcome. All right, so quick advantages and disadvantages. So as we saw yesterday, it works well with nonlinear relationships. We don't have to worry about any of our linear assumptions, any of our like normality, linearity, multicollinearity, none of that. None of that we have to worry about. We can pretty much take our data. We don't even have to scale for trees. Take our data, throw it into our decision tree model, and it'll work fine. Decision trees are also easy to interpret because you're basically traversing down a tree, and you can actually get those list of a list of steps of your trees. There's also implicit feature selection, because if a feature is not important at all, let's just say, with going back to linear regression, we had some features that had like a very high p-value because there's no significant relationship. The decision tree will just help you decide, okay, well, then we're not even going to make any splits on that dimension. So it's implicit feature selection being done. And then also it automatically accounts for interaction just by the sense of it looking at segmenting different, or it's segmenting segments of your data. And so that actually helps to account for feature selection as interaction as well. So disadvantages, again, as I've been alluding to the past couple of minutes, decision trees do tend to overfit, especially if they're completely pure. And by completely pure, I mean when all of your terminal nodes only have values from one class. So there's a lot of instability as well. Again, overfitting. Small changes in the input data can cause large changes to the structure of a tree. And then also, this is a quote from the book. I actually linked this book or its counterpart on our homeroom. Trees have one aspect that prevents them from being the ideal tool for predictive modeling, namely inaccuracy. And that's inaccuracy with regards to unseen test data, because again, the overfitting problem makes it very unpredictable when you have test data points that may look slightly different from your trained data points. So that brings us to ensemble methods. And the whole impetus of ensemble methods is wisdom of the crowd. So there's this whole like mathematical statistical experiment of this fair in England. There's this statistician that, those games where you're trying to guess like the weight or, how many jelly beans are in a jar, that kind of guessing game. And so people wanted to guess how heavy this ox weighed. And turns out everyone, when you're making one guess, you can be very near, very far off the answer. But when you aggregate a bunch of different answers together, it would be more accurate, basically. So the actual weight had only a 1% error from the median guess, versus if you were maybe to take like a root mean squared error of people's guesses, that would be much higher. And so the idea here is, even if individual people don't have too much knowledge on, I guess, the weight of ox, if you aggregate a lot of people's answers together, you'll get something that's pretty close to the actual value. And that's kind of what motivates the whole, field of ensemble methods. Basically, wisdom of the crowd.
So interestingly, there's a Planet Money episode that just came out. They're doing a series called Summer School in the month of August, and it's about that specifically. They went and tried to execute the same experiment. So if anybody's curious, Planet Money.
From Planet Money? Oh, yeah, that's awesome.
NPR. Yeah, it's a podcast.
That's very cool.
Yeah, just came out.
Yeah. Thank you for sharing, Taylor. I will tell you that like when I was teaching in person, I used to get everyone to like guess. I don't know. I used to get people to just guess random things, and then I'll look it up online. And it's very true that like individual answers themselves very, very off. But when you aggregate and take like the mean or median of the guesses, it's pretty accurate. Like I think one time I asked like distance from like Earth to the moon to like a class of 20 people. And I think the average of everyone's guesses was very, very close. Some people were like way up, way down, way lower than the actual values. But yeah, when you aggregate it together, and of course, the more guesses you have, of course, it'll like sort of converge to the actual value. But yeah, it's a really interesting, what's the word? Phenomenon. All right, so what can we take away from this? We can learn a lot by combining many different learners, and this is called an ensemble method. So in essence, we can combine the output of models that are not accurate enough on their own and get wisdom from a crowd. So how can we grow a forest of trees? You can see here they're continuing with that tree metaphor. Yeah. All right. So there are two main kinds of bagging models. And remember, today we're focusing on bagging models. Tomorrow we'll talk about boosting. Two main kinds of bagging models. We're going to talk about bagged trees, and then we're going to talk about random forest. And random forest is the one that's actually used, one of the most common machine learning models being used. And both of these have regression counterparts that I'm not going to talk about, but they work the same way. But they both have regression counterparts in case y'all are curious. Okay, so we'll start with bag trees, which is one of the algorithms that you can use in your project. So to conduct a bag tree estimator, what we need is first we bootstrap the entire data set. And we'll talk about bootstrapping in a little bit. Then we're going to build one tree using a bootstrap data set. And then we're going to repeat step 1 and 2 over and over again and aggregate all the trees. Kind of like what I was saying before, if you have like 4 different decision trees trained on like slightly different data, you can sort of have like a voting system to figure out. So if 3 trees tell you that it's 0, 1 tree tells you that 1, you'll classify it as 0. So yeah, output prediction through each tree. And for regression, you're going to take the average of the prediction, and for classification, take the majority predicted value. Like what I was just saying, you'll vote and see what the classification should be based on the output of multiple decision trees. And so it's called bagging because bagging is a combination of bootstrapping and aggregation. So bootstrap, aggregation, bagging. That's where that comes from. So what exactly is bootstrapping to start? So because trees are prone to overfitting, and this is especially true if the trees are built out to full purity in each leaf or each terminal node, to prevent overfitting, we're going to take bootstrap samples with replacement from our training data that is the same size as our training data. So we're just going to sample from our training data. And let's just say we have these, how many are here? 9 data points, 1, 2, 3, 4. Yeah, we have these 9 data points over here. And for each bootstrapped sample, basically the data are going to be used for each tree. We're going to sample with replacement from our original training data. So as you can see here, we have 3 bootstrap samples. And even though see there's only like 3 blue points, it's possible that some bootstrap samples might, have more blue points than the original sample because you're sampling with replacement. So imagine we have a bag of 9 data points where each time we're going to pull one out, take note of it, put it back. Take one out, take note of it, put it back. So that's how we create these bootstrap samples. And this is kind of like very minor, not minor, but this changes our training data. Of course, you're not introducing brand new data or anything, but you're sort of adjusting the proportions or the kind of the distribution of your data just a little bit so that your model won't overfit. Cool. So this is another example of bootstrapping. So let's just say this is our original data set of 1, 2, 3, 4. And in this case, it's a heart disease data set. And you have features like chest pain, blood circulation, blocked arteries, and weight. And of course, these are our target. This is our target variable of whether someone has heart disease or not. And then this is a bootstrap data set. So we're sampling with replacement. So the first one we sample, let's say we get 2, we get row 1, and then we get row 4 twice. That is possible. You can definitely, and you definitely probably will end up with a few duplicate rows as a result of bootstrapping. But that's okay because we don't want our decision tree to see the actual data over and over again. So this is the step of bootstrapping, which is a step done prior to training each individual tree in a bagging classifier. All right, after we bootstrap, then we aggregate. So once we've taken the bootstrap samples, we fit a decision tree to each sample. Now, each decision tree is going to have low bias, high variance. So each decision tree is probably going to be overfit. And then you're going to repeat this process for however many trees you want. Now we're doing the aggregation step. For classification, whichever class is predicted most by the bootstrap decision trees. So let's say you train like 100 decision trees on different bootstrap samples. It is likely that not every tree will give you the same result unless you have like a very, very like strong important feature set or it's like a very clear divide between your classes. But there's typically a little bit of difference between every tree. And so therefore you can have some sort of voting system to figure out what the actual classification is as a result of your 100 different trees. Cool. So as we can see here, this is a voting method. You can see that we have an instance of a random forest and it says random forest, but it works the same way for bag trees. We have 3 trees over here, and I guess you have n trees over here. First tree tells you it's class A, second tree tells you it's class B, nth tree tells you it's class B. You just do a majority voting, and then that's how you figure out what the final classification should be. And typically, when you have an ensemble method, the boundaries are a lot smoother. You don't really fit to every single like data point. Like if you had one data point that was like, what's a good example? If you have one data point that's like way out, like for example, over, let's see, do I have a better example? I guess not. So let's say I had like one yellow data point that's like out here. In a decision tree, the decision boundary might group all of these yellows and like, you know, fit to all the shape of all the yellow data points. But for a random forest, that data point might be one of the points of contention where, you know, some models might classify it as yellow, some models might classify it as purple in this case. All right. Any questions about that? Neat. So what's important to know is the bootstrapping, because if you were to just build decision trees on the same data over and over again, they're probably going to end up identical because of the top-down greedy approach that decision trees take. Cool. So bootstrapping and aggregating makes bagging. Cool. So, oh, this is exactly what I wanted to show you all. You can see that this is a decision boundary from one decision tree. And this is one with just bagging. You can see that the decision boundary is a lot smoother. So all of these data points that, you know, are kind of on the other side might just be like outliers or less frequent instances of the blue class that, you know, kind of can be yellow. So yeah, smoother boundaries protects from overfitting when you have an ensemble method like bagging. Cool. Questions at this point? Awesome. Okay, before we move on to the next one, I want to talk about out-of-bag error. So in general, only 2/3 of the observations will be trained on each model. That's because it can be very computationally expensive to perform cross-validation on bagged classifiers or regressors. Yeah, because you're going to be doing a lot of model training. Because imagine if you're building one decision tree and each one you want to do 5 cross-validation with 5 folds, and you're doing like 100 trees, and 100 I think is the default, or 50, that's the default. You're going to be running what 100 times 500 different decision tree models, and that can be very computationally expensive. One, is going to take a long time. 2, you're also storing a lot of the data, because every time you train like bagged trees, or every time you train a decision tree, it has to remember basically all the flow charts, like all of the conditionals for, you know, traversing down the tree. So it can get very memory intensive as well as computationally expensive. So in order to not have to do cross-validation on every single tree at every single node, we use out-of-bag error. And so every time you have an ensemble method, and this also kind of helps to combat overfitting in its own way. For every tree that is made, we use 2/3 of the bootstrapped sample. And so we train it on 2/3 of the bootstrap sample, test it on 1/3 of the bootstrap sample. It's kind of like doing a train test split within each tree that's being built. So if you actually take a look at, let's pull it up, bagged tree classifier. Let's get that scikit-learn. Okay. So you can see, oh, default is 10. Yikes, all right, I was way off. But here you can see you can get the out-of-bag scores. And you can get the out-of-bag scores just to see how well each tree is performing. So out-of-bag error, yeah, it's essentially just a simpler form of cross-validation that makes it more computationally efficient to do, you know, a bunch of decision trees at the same time. Right. So some issues with bagging. The issue with bagging is that each one of the trees might be correlated to each other. There might be one feature that is so powerful in generating a separation between different categories. So for example, if we had our iris data set, and we had something that looked like, where's my iris data set? This one, okay. So we had our iris data set, and this is a very, very strong split, right? Having x2 greater or less than 2.45. And if you remember what that data set looked like, we actually have it here, right? Right, if I have this dividing line over here, pretty much every tree that I make, because if you think about bootstrap samples, it's probably just going to be a subset of this pretty much, is going to find that I'm going to guess that almost every tree is going to start with a split over there. And so that means every tree is going to end up being very, very similar. And if you do have very easily separable data, all of your trees, even though you bag them, might still look the same. And so that's why we introduced random forest. Let me clear this. Let's go back to random forest. How do I quickly go through all of these slides? Okay, here we go. So yeah, having trees that are correlated with each other happens when you have very strong features like that X, like was it petal length or petal width, having that very, very clear separation there. So we need to do something to ensure that the bootstrap samples are not correlated with one another. And that brings us to random forest. So very, very similar. We start with bootstrapping. However, when we build our tree, we only use a random subset of features at each node from the bootstrap dataset. Not per tree. It's not like, okay, tree one, we're going to use the same 75% of your features. Let's say we have 4 features and we're going to use the same 3 features throughout the tree. Not even that. It's literally, if you have 4 features, at every node is going to randomly not look at one of the features. And that's how random forest introduces that randomness. So if you have 100 trees and we have that like X2, that petal width being extremely separable, if you have a random forest, not all of the trees are going to start with that first split. You're going to get some variation in your trees because you're doing a random subset of features at each node. So it's introducing even more randomness, therefore random forest, so that you overfit even less because you're making more changes to your data set. And so you're repeating step 1 and 2 many times and aggregate the trees. And same thing, you can also do a voting and you can also take the average of prediction for regression. So the only difference between bagged trees and a random forest is this step of taking a random subset of features at each node. And you'll see that this is actually extremely powerful because it allows for some of the features that might not, or that might be overlooked in a decision tree to be taken into account. Cool. Oops. All right. So for the random forest, you can see that for this bootstrap data set, let's just say that at the first node, it decides I'm only going to look at blood circulation and blocked arteries, and then I will build my tree from there. In another tree, it might say, okay, let's look at blocked arteries and weight, and your tree is going to look very different as a result. And remember, at each node, a different subset of features is being used, and you get to determine the number or proportion of features that's being looked at each node. Cool. All right. So random forests, they basically decorrelate each decision tree created via bagging by ensuring that at each split, only M features are considered for a given split. Now, the default is that M is the square root of, in this case, P, but P being the number of features, the total number of features in your data. So let's say if you have 25 features in your data, it's only going to look at 5 per node. So that means on average, this number of splits will not even consider a given strong predictor. As we increase the number of trees, this will not lead to overfitting, meaning that we should make as many trees as possible until we have achieved an acceptable error rate. So a new hyperparameter that you will play around with when you have pretty much any ensemble method is the number of estimators. So if we take a look at bagging classifier, the first one here, or second one here, is the number of estimators. So here, default equals 10. That means you're going to build 10 decision trees and then aggregate that result. It will be the same thing for random forest as well. Actually, let me just pull it up. Random forest classifier. Yeah, you can see, oh, for this one, the default is 100. But yeah, you can do like 100, you can do 500. The more estimators, the longer it will take. That's the main thing. As you can also see within bagging classifier, and actually not bagging classifier, but for random forest, because it is always built on decision trees, all of these parameters are the same as decision trees after an estimator. So max depth, min sample split, min sample sleeve. These are all the same as your decision tree parameters. So it basically defines per each tree in your forest, what are the parameters there. So these are things that you can tune as well. And then there is this one, max features, which will consider how many features to look at when looking at the best, when figuring out what the best split is. So I think, yeah, the automatic one or the default one will be the square root of the number of features. But you can also tell it like a specific number or a specific fraction or proportion as well. Cool. So this graph over here just shows different max features being used. And you can see it'll start to taper off. So in this case, it seems like the most effective one, the out of bag error rate. And out of bag error, if you remember, is that 1/3 per tree that is used as the test set for each tree. This is their error rate, and the lowest error is for square root of your max features. This might not be the case for every data set, but as you can see, the overall trend is that you start off with a little bit more sensitivity in your model or a higher error rate, and it starts to plateau off. And so in choosing the best estimators, let's say I was looking at the square root, I would choose an n estimators that, where it starts to taper off at the start of where it begins to taper off. So given this model, I would say maybe about like 90 to 100 estimators would be a good a number of estimators to use, but this is something that you can tune as well. Cool. So random subspace sampling method, just remember this, I've said a couple times, the M features are randomly chosen at each node, not for the entire tree. So let's say like 2 trees can start with the same split at first, but once you traverse down the tree, the nodes are going to consider different features for each tree. So extremely decorrelated based on that. So yeah, our trees should have diverse opinions. So to compare some performances, in general, random forests perform better than bagging, that perform better than decision trees. Now, this is only if you're looking at overfitting, for overfitting. So this has the out of bag error. So you can see here, we have the out of bag error and the test error. I know this is a little bit blurry, but the random forest ones are the blue one and the yellow one. So blue is lower than green. So the out of bag error is already better for random forest compared to bagging. And then for these, your test error, you can see that your random forest test error starts to plateau off, and so does your bagging error, but your random forest test error is a little bit better. So, but this is just in general. It does depend on your data set and also what you're using your modeling for. Cool. So some advantages and disadvantages. Very, very powerful. It will nearly always outperform decision trees. Basically, it is just less sensitive to changes in your data set because, combats overfitting with all of that randomness. Also, it is able to detect non-linear relationships very well, and it's harder than other models to overfit. There's so much randomness that's introduced in the modeling process, like in the bagging aspect, and also in the fact that it's looking at different features at every node. Very, very difficult to overfit. However, it's not as interpretable as decision trees. Actually, from your random forest model, you can actually pull out the individual estimators. So let's say that you have a random forest model with 10 trees. You can actually pull out each of the 10 trees and then print out their, the flow chart of how the data points traverse down the tree. You can actually get that data. However, if you have 100 estimators, you don't want to go through all of that. But if you wanted to, you can. And there are also many hyperparameters to tune. I don't know if that's a disadvantage, but it's kind of like a tedious process for data scientists, I guess. So grid search will be your friend when you're looking at random forest. So if we take a look at random forest over here, some things I want to point out, because I won't be going through code today. Some things I want to point out is attributes. From our attributes, you can see that you can actually pull out our estimator. You can pull out I think it'll be like a list of decision trees if you wanted to look at each decision tree and like plot their results, or maybe you want to run your data through .predict of each decision tree. Not necessary, but you could do that if you ever wanted to. You can find out their out of bag score, and also, oh yeah, this is what I was looking for. You can also get feature importances. You can get feature importances of your random forest. So something that I actually want to do really quick, since I think we have a little bit more time, I want to show you all this in how this compares to a decision tree. so we have our decision tree up here. I'm going to just import the random forest and then just do this. And we're gonna fit it. Hopefully it doesn't break. DLF.fit xtrain ytrain. Let's go with the max step of 5 first. Okay, these don't break. There we go. Never mind. If this doesn't work now, I'll do this again at a different office hour, but I don't want to work through this right now. Anyways, what I wanted to show is that this feature importances graph over here shows a lot of importances. So as you can see, like 90% of importance is on petal length. So you can sort of infer from this that this decision tree model is overfitting to petal length, which, I mean, maybe that's just the nature of it, but maybe it's just because of its top-down approach. Typically what you tend to see with a random forest, when you look at their feature importances, it'll actually even out the importances across different features a little bit more, because it is by its nature considering just more features, over all of its decision trees. So typically in a random forest, you'll see a little bit more smoothing in the feature importances. You'll see at least, like, I'm sure these will increase in value a little bit more. I do want to take a look and see what's going on up here though, real quick. Any questions? I'm using the wrong data set. Any questions at this point? Xtrain iris and ytrain iris. Okay, neat. Okay, so we take a look at clf.feature importances. You can see that just by the numbers, it's a lot more spread out. And actually, let me just plot it in the graph. X iris.columns, and we want to look at clf.feature importances. There we go. So as what I was trying to say earlier, this one had like 90% of its importance on petal length. But in this case, you can see it's a little bit more even over the 4 features that we have here. Hopefully you have more features than this in your project, so you'll see that effect a little bit more. Cool. All right, so some of the hyperparameters, you have n estimators, the number of trees in the forest, criterion, the same as decision trees, and actually the rest of these are same as this. Oh, actually, no. This one is the same as decision trees. Max features, the number of random features to be considered when looking for your best fit. This is the one that's by default the square root of the number of features that you have. Max depth, that's something that's similar to decision tree. Bootstrap, you can actually choose not to use bootstrap samples and just using your regular training set without bootstrapping, but you still have the randomness of feature selection at every node. So if you just want to see how that works, you can do that too. You can get your out of bag samples and also n jobs. N jobs is something that I did talk about. It's not really related to the model, but it talks about your computational power. I personally don't know too much about this myself, but if we take a look at n jobs, where is it? N jobs over here, the number of jobs to run in parallel. And this is basically how your computer trains all of these decision trees. I think the default is 1, so it's just using 1 core to train your trees or train your model. If you're finding that it's taking a very, very long time, you can increase that number. I think it depends on the number of cores in your computer. I think like most computers, like 4 or 8, maybe, I don't know. But if you're finding that your models are taking very long and you're not running too many other things on your computer, you can use -1 to use all the processors on your computer. It'll just run faster and run more things in parallel, basically. So if you're curious about that, not all models have this. I know this one does. Bagging classifier also has this as well. So yeah, that's in case y'all were curious what n jobs is. Sweet. Okay, here. I should have looked ahead at the slides before showing this, but basically, the more the accuracy of the random forest decreases due to the exclusion of a single variable, the more important that variable is. And therefore, variables with a large mean decrease in accuracy are more important for classification of data. Basically, what they're trying to say here is more important features help to reduce the criterion more. Basically, more important feature helps to contribute to more purity when you split on that feature. And so that's where feature importances come from. But by default, that is how scikit-learn computes feature importances. There are actually other feature importances, other ways to compute feature importances. You can check out that link there if you're interested, but usually the default one is good enough. Okay. On another note, you can also create custom ensemble methods by making use of voting classifier or voting regressor. And this is intended to be used with conceptually different models. So for example, let me pull up voting classifier real quick. Okay, so in voting classifier, you give it a list of tuples with, I guess, the name of it and what the estimator object is. So let's say, so far we've learned decision tree, naive Bayes, we talked about k-nearest neighbors and logistic regression. If you want to throw them in a voting classifier, like what I was mentioning at the very start, the simplest form of ensemble method, you can instantiate those 4 model objects, put them as a list of tuples, and feed them into the voting classifier. When you instantiate the voting classifier, it'll basically do how I described the process earlier on. Run your data through each of the 4 models and then do some voting. And you have a lot of the similar hyperparameters as well.
So this is separate from the voting that the random forest itself does on the
Yes,
output?
this is separate from the random forest voting because the random forest does the voting on its own. Well, it does the voting for you when you fit the model.
Gotcha.
Oh, there's something else that I wanted to. Oh yeah, okay. In the bagging classifier, if you were taking a look at this this documentation, you can see here that base estimator is a parameter. And basically it is the base estimator to fit on random subsets of the data set. And if none, the base estimator is a decision tree. So by default, a bagging classifier is going to use a decision tree. However, this is saying that you can give it other model objects as well. So if I wanted to bag naive Bayes models, I could do that. You could just instantiate a naive Bayes model and then feed it into the base estimator argument here. So you do base estimator equals to like naive Bayes, like Gaussian naive Bayes, or you can do k-nearest neighbors as well. Maybe k-nearest neighbors will have a big change when you do bootstrapping. I don't know. So just some like details. I would say for this project or for this phase, you don't have to worry too much about changing or experimenting with different base estimators because it was conceptualized with decision trees in mind, but just good information for you all to know, I think. Neat. All right. So that is all for bagging models. Now, bagging again is just one subset of ensemble methods, voting classifiers being another subset. Tomorrow, we're going to talk about boosting methods, which is a different kind of ensemble method. So yeah. With that, does anyone have any questions? I don't have any more slides. Yeah, the next slide is boosting. Yeah, I don't have any more slides on this. Does anyone have any other questions? All right, well, I'm going to start slacking people if I don't see your blogs. So expect to see a Slack from maybe you haven't submitted your second blog yet. So please do that. Also, I've been getting more functions. So thank you all for sending that to me. Happy to talk through your functions. What's really interesting is I'm seeing quite different functions from all of you. So I'm excited for that variety, but all of the functions I've seen so far work fine. So if you haven't sent it over, please do. I am keeping track of who sent me what. But yeah, if there are no other questions, going once, going twice. All right, well, if there are no other questions, I will talk to you all tomorrow at this time and we will talk about boosting methods. All right, have a great rest of your day, everybody. Bye.